So good afternoon and welcome to the Communication Signal Processing Seminar. So I should first start by thanking Shelley Felkamp and Catherine Goodwin, who are the people behind the scenes to make sure this works well. So I'm delighted that our speaker today is Peter Bartlett. So Peter is a professor of computer science and statistics at the University of California, Berkeley. He's also the associate director of the Simons Institute for the Theory of Computing, the director of the Foundations of Data Science Institute, and the director of the Collaboration on the Theoretical Foundations of Deep Learning. His research interests are very broad. They include machine learning and statistical learning theory, and he's a co-author of the book Neural Network Learning, Theoretical Foundations. He has been an received several prizes, including he's been an Institute of Mathematical Statistics Medallion Lecturer, winner of the Malcolm McIntosh Prize for Physical Scientist of the Year, and the Australian Laureate Fellow. And he's a fellow of the IMS, fellow of the ACM, and fellow of the Australian Academy of Sciences. Today he's going to tell us about benign overfitting. So I'll give cede the floor to Peter.
Thanks, Vijay. Thanks very much for inviting me. So let's see if I can make this work again. There we go. So is that working okay?
Yes, yes it is.
Hard to tell with Zoom. Okay, so yeah, so very happy to be here. Thanks for the invitation. So this is joint work with Phil Long at Google, Gabor Lugosi at Pompeu Fabra, and Alex Sigler, who's a PhD student in statistics at Berkeley. And it's about this phenomenon of benign overfitting that's really emerged from deep learning practice. So these deep neural networks, it turns out, can be trained to zero training error for a regression loss. So they're interpolating every data point and still give good predictive accuracy, something close to state-of-the-art performance, even when you know there's noise in the problem. So the labels in the training data can be corrupted. This is an example where there's some percentage of corruption at this end of the scale. On the x-axis here, it's fully noise in the labels. There's no signal at all. And this is looking at 3 different networks and how long it takes to reach a point where they're giving effectively zero training error, and the performance in terms of the test error is degrading only slowly as the noise level is increased. That's quite an astonishing phenomenon. I guess been observed by a bunch of people. There was this group based at Google, and Misha Belkin and collaborators had similar observations, not just in deep neural nets, but in other prediction methods. This lack of a trade-off between the fit to the training data and the complexity of the model is particularly surprising. I'll be a little more specific about that in a moment. So it's certainly overfitting in the sense that we're getting a perfect fit to the data. You couldn't imagine anything that fits better, but without any effort to. But this sort of overfitting is benign in the sense that the predictive accuracy is good for these methods. Okay, so I think that's a really striking phenomenon. Statistical wisdom tells us that we should be trading off the fit to the training data, often represented in terms of something like empirical risk, the average of the across the training sample, let's say of size n, of the error in our prediction on a certain XY pair, measured here by the quadratic loss. We should be trading off that fit to the training data with some notion of the complexity of this prediction rule f hat, whether that complexity is measured in terms of the number of parameters that we're adjusting based on this data, the norm of some parameter vector, maybe the norm in some reproducing kernel Hilbert space, or some parameter of some other non-parametric method. We're taught that this is really important to have this kind of trade-off, particularly for non-parametric methods like deep neural networks. We teach our undergraduates that this kind of interpolation, fitting too well to the data, is a bad idea. It'll lead to a function that's not a reasonable estimate. And you can find examples everywhere of this. So I think this is really a new phenomenon, getting good predictive accuracy even though you're fitting to noisy data perfectly. There's been a huge amount of work. This is something that emerged from discussions at a program in spring 2017 at the Simons Institute, and a whole group of folks got excited about this phenomenon. There's been an enormous amount of work since then in a bunch of different directions. I'm not going to try and review that. I mean, I'll point to a few particular cases along the way. Just to kind of summarize the viewpoint that emerges in all of these cases where we have some rigorous understanding of what's going on in these settings. The intuition is that this phenomenon occurs when the prediction rule f hat can be decomposed into two pieces. One that's a simple component that's useful for prediction, and one that's a spiky component, a complex thing that's useful for overfitting, but it doesn't have much of an impact on predictive accuracy. So, the first component, that simple one, is, really still within the domain of classical statistical learning theory. And in the sense, that the statistical complexity is small in that component when you're predicting well. And the other component is somehow outside that domain. It's not useful for prediction. It's good for overfitting, but it's benign. It doesn't have a negative impact on predictive accuracy. And we'll see a few different examples where this sort of decomposition arises, in a precise way. Oh, and just to advertise, so we have this with Andrea Montanari and Sasha Rachlin. We have a review paper about particularly these aspects of the statistics of deep learning that's going to appear in Acta Numerica this year. Okay, so one of these examples where we can see benign overfitting is in kernel smoothing. So, a Nutter-Watson smoothing method takes some kernel, which is, a function of how far, if you want to evaluate your prediction on a point X, you look at how far it is from a training point Xi, and you weight the corresponding Yi according to some function kh of this difference, and it's a weight, so it's a convex combination of these Yi's. These kernel functions are positive, and h here is a bandwidth that tells you, how far away you should be considering the training points. Okay, it's a very classical method. If you consider singular kernels, so instead of doing something sensible with this kh, you have it go to infinity at 0. It means that the weight that you're imposing at a training point xi goes to 1, because the infinite value down here in the limit is going to be dominating, and so you'll have an interpolating prediction rule. So for example, if this kernel is 1 over the norm to some power, suitable power, so that things integrate, and it's compact, then although these kernels seem kind of crazy, they're super spiky at 0. For a suitable choice of the bandwidth parameter, it turns out you can get minimax optimal rates here. This was shown in a paper of Misha Belk and Sasha Rachlin and Sasha Zibakov a few years ago. So that's quite a striking phenomenon. In this case, this kind of decomposition that I'm talking about, the f hat 0, is something that you would get from a kind of classical Nutter-Watson kernel smoother with just a standard compact kernel, and the spiky piece is what you see because you're superimposing on that this big singularity. So that's something that allows you to interpolate, but it has a small L2 norm, so it doesn't affect the predictions. Okay, so that's one nice example. A lot of the rest of my talk is focused on a simple linear regression setting, where we have a fairly complete understanding of when this sort of benign overfitting occurs. So I'll say a little bit about precisely what the setting is that we're talking about, and we'll get to this phenomenon of adversarial examples that's been observed in deep learning, and what how it is manifested in the linear regression setting. We'll look at generalizations going across the whole spectrum, from interpolating through under-regularized linear prediction rules through to kind of classical levels of regularization. And then we'll look at some shortcomings of model-dependent bounds. So what standard statistical learning analysis can and can't tell us about these sort of benign overfitting settings, particularly with a focus in the linear regression setting. Okay, so let's start with the formulation of these linear regression problems. And you know, I guess before I do, the point here is really to understand this benign overfitting phenomenon. It's not to advocate interpolating training data, and if you're trying to solve a linear regression problem, it's trying to find the simplest setting where the phenomenon arises and try and see, you know, what's behind it and when it does and doesn't occur. Okay, so we've, just to fix some notation, we've got a covariate vector X, and we can think of that as being infinite dimensional or some large dimension. We've got a response, a real valued response Y. This XY pair, the assumptions we need are that it's they're from a sub-Gaussian distribution, and it means 0. Things are well specified. So the conditional expectation of Y given X is a linear function. Actually missing from here is there's a small ball condition that you don't have the distribution of the X's too concentrated. And some important notation, there are 3 things that it'll be good to keep in mind through this part of the talk. The covariance of the X's, we're going to consider a spectral decomposition and look at their eigenvalues, and let's define them as lambda 1, lambda 2, and so on in decreasing order. These are crucial. We don't care so much about the eigenvectors because everything is kind of symmetric for the estimation methods we're considering here. Theta star is the parameter for the best linear prediction, so the minimizer of this expected squared error, and sigma squared is its expected squared error. So this is the noise level in our problem. Okay, so these are three pieces of notation that's important to keep in mind. Now we're going to consider a particular interpolating linear prediction rule, motivated by the fact that if you're working with a stochastic gradient method, as deep learning approaches do, or working with I should say gradient flow on a convex criterion like a quadratic loss, and you start at 0, then you will finish at the minimum norm interpolating solution. So we consider the minimum norm linear interpolant. So we have our data, think of it as n rows of a matrix. I'm going to use matrix vector notation, even though we can be in an infinite dimensional Hilbert space. So X is our data with these n rows, Y is our vector of responses. We have the minimum norm interpolant. We can think of that as solving this, minimize the squared Euclidean norm of our parameter vector, subject to the constraint that the fit to the training data in this squared error sense is the best possible, right? Min over all parameter vectors beta. We're going to be in the situation where the dimension, the rank of our data matrix X is big enough that we can find an interpolating solution. So this is always going to be 0, and we're finding the minimum norm interpolant, which has this specific form. I mean, you can write it as X pseudo inverse Y. I'm writing it out in a way that's suggestive of a linear regression in the classical parametric regime, X transpose X inverse X transpose Y. We take a pseudo inverse that zeroes out, all of those, minimizes the norm by zeroing out all of the directions that we don't see in the data. Okay, so that's the estimator that we're considering here. The criterion of interest is the excess prediction error, by how much our expected squared errors exceed the best possible, which is what this theta star vector provides. And it's an easy calculation to see that this is just the expectation of the x's in here. Give us this is just the theta hat minus theta star transpose sigma theta hat minus theta star. So this quadratic form defined by the sigma tells us the impact of our estimation error in estimating the parameters, the true parameters theta star. We come up with this theta hat. So there are some directions here that won't matter at all because we've got very low variance in those directions, and it doesn't matter what our estimate looks like in those directions. In the high variance directions, of course, it matters a lot. And this is why we're focusing on these eigenvalues. They tell us the extent to which these different directions are going to be important for predictive accuracy. Okay, so that's the criterion that we're interested in, this excess prediction error. So let me tell you about the result, the main result here. So we're considering minimum norm interpolating prediction rules. So you can think of that as the limit as this lambda goes to 0 in a ridge regression problem. So we have this is the empirical risk, and this is a regularizer that's ensuring that we get a nice small norm of our parameter vector. If you think of the limit as lambda goes to 0, that's the problem we're solving. We're driving this term to 0 and minimizing that term. You can think of that regularized optimization problem in terms of an equivalent constrained optimization problem. You might, and this is a kind of classical approach, you might think of it as defining a constraint on the size of our parameter vector. This defines a class of linear functions, and we might be interested in the extent to which empirical risk differs from true risk across that class, because this is what we're minimizing within that class. Another equivalent way of defining the problem is to say, well, let's minimize the norm of our parameter vector subject to a constraint on the empirical risk. We want it no bigger than some constant. Of course, these are all equivalent for appropriate choices of these constants, data-dependent choices. But the case we're interested in, we're thinking, of course, of the last one, but when the C that we impose here is way smaller than we should expect, right? So we're thinking of under-regularizing, or equivalently getting a fit that's too good to the data, in the sense that this C is much smaller than the best possible, right? The minimum of the expected squared error, which this is an empirical estimate of. So in particular, we're interested in this first part of the talk in the case where C is 0. Okay, so that's the overfitting regime, where this best possible empirical risk is 0, and our estimator now is minimizing the norm subject to that constraint. So it's getting, interpolating every data point for each xi yi pair. We have our theta hat, so that xi, the inner product between xi and theta hat, is equal to yi. So we're nailing every data point, and really, you can think of that as, well, there's this noise, and the level of energy in the noisy labels is proportional to n. So we're taking all of that noise energy and we're embedding it in theta hat in some sense, right? And the question is really, when can we do that without hurting predictive accuracy? Okay, so here's the result. It's for, and I think we're again missing the conditions on these linear regression problems. So I guess I've said for any linear regression problem satisfying those conditions that I described on the earlier slide. There's a sub-exponential and small ball, sub-Gaussian and small ball condition. Okay, so for any linear regression problem, there's a theta star sigma squared and these covariance matrix, in particular its eigenvalues. We want to have the eigenvalues such that we see the data is going to span an n-dimensional space. We're going to see a high enough rank in our data matrix that we can interpolate, and if the so the result is in terms of two notions of effective rank. So ignoring that for the moment, this is some quantity that's telling us about the effective rank of the covariance once we ignore the k highest variance directions. So let's ignore those high variance directions and then look at this remaining subspace, the orthogonal subspace, when its effective rank is large compared to the sample size n. All right, that defines, k star is the dimension of this high variance subspace. At that point, we can say with high probability over the training data, the excess risk, so how close to optimal we are with this minimum norm interpolating linear prediction rule, is bounded by something proportional to a bias term. I'll get to that in a moment. And a variance term. This is really the interesting one, because it's the noise that we're fitting to here. The variance term has a k star over n penalty for this first subspace, the heavy subspace. And then there's another component n over capital R k star, which is another notion of effective rank of this remaining subspace. So we better have that effective rank big compared to n. In particular, this means that the dimension of that subspace should be big compared to n, the sample size n. Okay, and then on the flip side, in fact, in order to get the bias terms to align, we need some additional symmetrization. So you can say, if we have lots of independence in the x's, if we choose our theta star as a symmetrized version, so flipping signs randomly, then the expectation under this randomization of the excess risk is exactly the same thing modulo constants. There's some multiplicative constants there. So we can't hope to do any better than this, even down to the specifics of the bias term. And I'm not focusing on it here, it's in small print. It's the bias term here depends on the specifics of this parameter vector and how it aligns with the eigenvalues. Anyway, I'm skating over that. So what are these effective ranks? What do these really mean here in these definition of the low dimensional subspace and the high dimensional part? Well, they are two different notions of effective rank. The little rk is after you ignore those first k biggest eigenvalues, what's the L1 norm of the remaining vector of eigenvalues divided by its L infinity norm. So how many of these biggest eigenvalues can you fit in the sum of the others? All right, and the capital RK is a similar thing, but it's L1 norm squared divided by L2 norm squared. Okay, so just slightly different notions of effective rank. They're pretty closely related to each other. You can show that they're not too far apart. That's a kind of easy calculation. And just to get some intuition, if we think about the effective rank of a diagonal matrix, it's just the rank of the matrix. So, if things are isotropic, then these effective ranks are just the dimension that we're left with after we take out the first k star. And, if we don't have this symmetry of the same variance in every direction, then we get penalized for that. The rank drops somehow, right? So it's the most symmetric case that's the highest rank, highest effective rank. And, as the symmetry drops, two different notions of symmetry for these two different notions of effective rank. As that symmetry drops from 1 down to as small as 1 over p, then the effective rank drops. Okay, so that's the definitions and sort of some of the intuition behind these effective ranks. And so what that means is we're choosing this k star so that notion of effective rank, the L1 over L infinity of the remaining eigenvectors, the tail of the eigenvectors, when it first exceeds the sample size n, that defines this first subspace, and then we're interested in the effective rank of the remaining subspace. So we better have k star small compared to n. It appears here in the variance term. And we better have the effective rank of the remaining subspace large compared to n. This is precisely when we'll get benign overfitting. Okay, and so in terms of this intuition that I presented earlier, our interpolating linear prediction rule decomposes into an F0 hat term and a delta term. The prediction component is this k star dimensional subspace, the one corresponding to the highest variance directions, where the k star is determined by, what's the effective rank of the orthogonal subspace. When does it first get large enough? And the overfitting component, the spiky component, is the orthogonal subspace, right? So it's this the subspace corresponding to lambda k star plus 1 and so on. And it's going to be benign it's going to have a small impact on our predictive accuracy, provided that that effective rank in that subspace in terms of this capital R K star is much bigger than n, because we have an n over capital R K star term. Okay, so that's how things split up in the case of linear regression. Why does it look like that? Well, the mix of eigenvalues of this covariance matrix tells us, we've seen it tells us how the errors in our our estimate of the parameter vector affect prediction accuracy, but it also tells us how the label noise gets distributed across our parameter estimate theta hat. We'll see more of that noise in the high variance directions and less in the low variance directions, and it's the balance between these two effects that determines the predictive accuracy of this minimum norm interpolating prediction rule. So yeah, the kind of bottom line is we need that noise energy that's taken from the labels and injected into our parameter estimates to be distributed across lots of unimportant directions, these small lambda I directions. So, this is really a high dimensional phenomenon. We need overparameterization. We need far more parameters than sample size in order to get this n over RK star to be nice and small. We need to be in a very high dimension. Lots of parameters that are unimportant, somehow equally unimportant. So large number of non-zero eigenvalues. They shouldn't have too much energy. There shouldn't be, and there should be many small ones. So roughly equal is even better. Okay.
So Peter, just a quick question on the thing. So I was just trying to understand the result in a way. So so you have two parameters. One is the sigma, and that the eigenstructure of sigma, and then you have n the number of samples in some ways. Right? So
right.
So I was trying to understand where the parameters come in the sense of where does
in the bias
instance is given problem instance in the bias term.
Yeah, so it's so they really don't. We have a sort of this variance term. I mean, I'll say a little bit about the proof in a moment to give you a bit of an idea of why I talk about them as bias variance terms. This term, is what it is. The bias term depends on the scale of the parameters. That's where those theta stars arise. They arise because our empirical view of the covariance isn't quite the covariance, and that's where the signal goes, the theta star inner product X. In the training data, we get a distorted view of theta star because we see data that's not that has an empirical covariance that's a little different from the true covariance. This term is purely due to the noise, the energy from the noise. So yeah, so those parameters arise in the first term, and I'm sort of sweeping that term under the rug, but I did include it down here. One interesting thing when you think about the parameters in this k+1 to infinity is the orthogonal subspace, right? So this k star dimensional subspace is where all the action happens. That's where you're doing all your prediction. The bias term has just the same bias from the remaining subspace as if you'd predicted 0, as if your theta hat was 0 in that subspace, in that direction, all those directions. So this is kind of since that appears in the upper and lower bounds, you're not doing any useful prediction in that orthogonal subspace. But it may be that bias is terrible if, for instance, there is some useful prediction to be done there, right? If the optimal theta star is enormous in that direction, you're going to be falling short of the optimal linear prediction rule then. Does that answer your question?
Yes, yeah, thank you. Yeah.
Right.
While you're on that slide, can I just ask follow up? So I think you were making an argument that your bound is somewhat tight by this lower bound. I didn't quite follow the argument with the random sign flips. Would you mind?
Right. Okay. So the two extra things that we need are that not just that X is sub-Gaussian, but that X can be written as a linear transformation of a vector with independent components. So that's stronger than sub-Gaussian. So, you know, for instance, you know, if a Gaussian X satisfies this condition.
Sure.
And the other thing that we need is that for the lower bound is that for any given magnitude in these different eigenvector directions of theta star, I want to, you know, I can only say something here if I have some symmetry. And I introduce that symmetry by saying, well, my theta star actually is randomized in its sign in those different components.
Okay.
You know, that's it. And in that case, we can prove this lower bound, which tells you, you know, so the bias component just depends on the components squared of these theta stars. You know, I need some additional symmetry to prove the lower bound.
Okay.
So yeah, it tells you, for instance, with Gaussian X's, and if you're choosing your theta star to have a certain pattern of magnitudes of all of the components and you randomize across those, then you get precisely the same quantity. So, you know, you shouldn't expect to do any better than this upper bound without some additional information about the theta star or without some other extra dependence that's somehow helpful. And for instance, is not there in the Gaussian case.
Got it. Thanks.
Sure. All right. So, so we were up to this point. How are we doing for time? We got plenty of time. Okay. So just to give you a little intuition behind the proof where these two terms come from, you know, you can think of the excess expected losses coming from the signal part and the noise part. The signal part is this inner product between X and theta star, and the noise is everything else. I mentioned this earlier. We get a distorted view of theta star because we don't have, because our sample has you know, a particular geometry that doesn't quite match the covariance, the geometry determined by the covariance. And of course, the noise is corrupting things. So that first contribution, the signal contribution, is not as interesting. It's, you know, even in high dimensions, this is not a problem. The noise is the part that's a problem, because we're taking all of the energy from the noise and injecting it into our estimate, theta hat. Okay. So yeah, so we do this sort of bias variance decomposition, break things up into these two pieces of Y, the signal part and the noise part. And so you can break up the estimate into, you know, the part that's due to theta star and the other part, and then look at the excess risk of those two pieces, right? And show that it's, you know, there are two parts to it, a signal part I won't say any more about, and a noise part, which is the interesting one in this case when we're interpolating. And, you know, writing that excess risk, breaking it down into the different directions, the principal component directions for our data, we've got this split into the heavy directions and the light ones. You know, and when we think about the light directions, this condition that defined the prediction subspace, that's a condition that ensures that all of the eigenvalues of our covariance, of our empirical covariance in this orthogonal subspace are nicely concentrated. They're all about the same, you know, within a constant factor. This is just like a very standard matrix concentration result. And you know, that means that we're getting something that looks like a component of the identity in that subspace. So you know, all of those eigenvalues are at least this rho, which is the sum of these, the tail of these eigenvalues. And you know, when we take this pseudo inverse, right, that's like, you know, we're zeroing out all of those other directions we don't see, but in the n directions that we do see, it's like we've got this rho component in all of those non-zero directions. So it's very much like a ridge regression setting. Okay, and you know, you can kind of track through where the energy from the noise goes. If we think about an eigenvector direction, that'll see a noise energy in this sample that's proportional to you know, the scale of the x in that direction, which, you know, square it, it's lambda I, and proportional to n. That's scaled through this inverse operation by no more than rho to the -2, where rho was the scale of this these eigenvalues in that direction. squared because we're talking about energy. And then of course, you know, that gives us the energy in a particular direction of this error, and to convert that to prediction error, we should scale it again by a factor of lambda I. Okay, so we get that our prediction error looks like, in that direction, we get a contribution to prediction error that's sort of like n lambda I squared divided by rho squared. Turns out in those first k-star directions, we can do a little better, and in the rest, we just add everything up and get an n over this rank. You know, this is kind of the whole story. The whole story for the upper bound, I won't go into the lower bound. It's essentially the same thing. Okay, so so great. So we have this this result, and now you could ask, well, what happens? You know, what are situations where, as the sample size grows, we're going to do well? We're going to get our excess risk getting smaller and smaller. What does our covariance have to look like for that? So I'm actually going to look at a simpler problem where we get an upper bound on the bias that doesn't depend on the specific properties of theta star. So we can focus just for a fixed norm, let's say theta star, we get an upper bound that applies that can give us information just about what it is about sigma that means we can cope with any theta star. That upper bound has this form, you know, not so important, and we define things as asymptotically benign if in the limit, you know, the bias term or this upper bound on the bias term plus these other variance terms all go to zero, right, as the sample size grows. And I've written an index n on the covariance matrix because, you know, it turns out that the infinite dimensional case with a fixed covariance matrix is not that interesting. So if you look at for instance, a particular rate of decay of a particular infinite dimensional of an infinite dimensional covariance operator, that decay is a polynomial decay, and I need to add some log factors. If you have a polynomial decay, you need an exponent of 1, and you need a log factor to make the whole thing integrable. That's an if and only if. So, you know, the only case where we get this benign behavior in the infinite dimensional setting is this very specific and rather slow decay of the eigenvalues, you know, just at the edge of converging. And that's kind of the only, you know, it's an if and only if, right? So that's the only rate at which these things can go down. So that's sort of surprising. So we could consider instead a sequence of covariance matrices of varying dimensions. And then it turns out that this is a much more generic phenomenon. So if you restrict to a finite dimension, you have, for instance, fast decay of the eigenvalues plus some constant level of noise in all directions, then as long as the dimension that you truncated at is large compared to the sample size, and the total energy in that constant piece is small compared to the sample size, but not too small, right? We can't truncate at some finite value. Then we get benign overfitting. We get this nice condition on the eigenvalues that as the sample size grows, we're getting better and better in our predictive accuracy, and you can make that quantitative. Okay, so that's a more generic phenomenon, right? If you've got quickly converging eigenvalues plus some small thing in all directions, and the dimension is finite but large compared to the sample size, then you get benign overfitting. If you have a slow decay of the eigenvalues, but you truncate it at some point so that you know, it's a summable sequence, and again the dimension is large compared to the sample size, then you'll have the same thing arising. Okay, so it seems like it's a much more universal phenomenon in the finite dimensional case where you truncated a certain dimension that's necessarily large compared to the sample size. Okay, let me say a little bit about adversarial examples. This is a phenomenon that's been observed in deep learning where, you know, you can have a network that's trained and predicts very accurately, and then some very small perturbation of an input can turn a confident classification of, you know, a pig into a prediction that it's confident and correct classification of a pig into a confident and incorrect classification that it's a plane. You know, this is I think very widely known and a surprising phenomenon. In the linear regression case, it's really clear why this should happen. You're taking all the label noise and you're putting it into these parameters. So there's some direction where you've got this proportional to n energy appearing. It gets translated in this way, the noise component into the very large magnitude direction. And if you then go perturbing an input in precisely that direction, then the lower bound that you see is like 1 over a term that's in the upper bound on the excess risk. So if you're doing this minimum norm interpolation and your excess risk is small, then your sensitivity to a perturbation of the input is necessarily large. There's no trade-off, right? Benign overfitting is leading to huge sensitivity in this sense. That makes a lot of sense from this intuition about having these two components, a prediction component and an overfitting component. That overfitting component has to have small L2P norm if you're in this benign overfitting regime, but it has to fit all of the noise. So it has to have a large L infinity norm. So, it's by its nature a very sensitive kind of a function. Okay. We can extend these things to the ridge regression setting. This is joint work with Alex Sigler. So, we thought about the case where I've been talking about the case where lambda equals 0. There you're interpolating, but I guess it's the limit as lambda goes down to 0. You're interpolating, but minimizing the norm at the same time. If you have a very small value of lambda, you'll be close to that solution. We can consider here the whole spectrum of these prediction rules from overfitting as much as possible, that is interpolating the data, to more classical levels of regularization, going through, under-regularized at various stages. I'll show you can get the same kind of tight bounds on bias and variance. The message here is that these effective ranks are replace the sum of the eigenvalues just has a lambda augmenting it. So you're kind of blowing things up with this regularization. One surprising aspect, if you consider the x transpose x plus lambda I inverse x transpose y solution to this optimization problem, you can understand the cases where the optimal lambda is actually negative, and there are those cases. There are cases where, if it turns out the effective rank in this orthogonal subspace is really large compared to the sample size, then there's a very significant bias in your covariance estimate, and you can decrease that bias by introducing a negative lambda, and that doesn't significantly affect the variance. So it's kind of very non-classical situation that such a thing arises here. And as I say, you get, the whole thing just includes extra lambdas in all of these eigenvalue sums that we see. A very explicit upper and lower bounds of exactly the same form in the ridge regression setting. Okay, and then finally, let me just say a few words about what classical statistical learning theory sort of approaches can say in this benign overfitting sort of setting. So what do I mean by that? Well, so the kind of approach that we're used to in analyzing learning methods of this sort, there's been a long history of analysis of classes of functions like those computed by neural networks. We are in a situation, we've got an algorithm that returns a prediction rule that's got nice performance on a training sample, and maybe it's simple in some sense. Maybe for a deep network, there's a small product of spectral norms of the matrices of parameters in that network. We want to know, when's that good enough to ensure that the expected loss is nice and small. And maybe we're interested in a bound that depends on properties of that prediction rule, like these small spectral norms in the deep network case, and depends on the sample size n. Okay, so this is a very standard sort of setting, and a standard approach in this setting is to go via uniform deviation bounds, where you say, maximized over some class of functions, and maybe it's the class of functions that have a suitable bound on this product of spectral norms, for instance, right? So maximized over that class. Empirical risk, so sample averages of loss, are close to expectations, And if they're close and we have a nice small value here, you know, we'll have a near minimal value here. And so we certainly get an upper bound of this form by considering uniform deviations across a class of functions of this kind. So that's one family of bounds that suffice to give us information about the performance of a prediction rule. So there are these nice results, recent results of Nagarajan and Coulter that show that, you know, sometimes these uniform deviation bounds certainly cannot help in these overfitting settings. They came up with an example of a classification problem where you could, with a naive Bayes algorithm, effectively, you can have a function that in this classification problem gets every training example correctly classified. It also predicts accurately, you know, according to the distribution that they came up with, but the symmetry of that distribution implies that, you know, any uniform deviation bound for any class of functions that contains a function that you're likely to see, let's say, you know, has to be large. So it's kind of hopeless to hope for any bound of this sort to give you any useful information on the expected loss of the prediction rule in this case. So, you know, that was a very illuminating example. So what I want to tell you about is a result that has a similar flavor in a regression setting, where we're talking now about any model dependent bound. So not uniform deviation bounds specifically, but anything that relies on properties of the prediction rule in the linear regression setting. So all we're seeing is this parameter vector. And, you know, the result is that a model dependent upper bound of this sort is necessarily loose if it's sufficiently broadly applicable. Okay, so I need a couple of definitions for this. The first is that it's a uniform. So we're thinking about the least norm interpolant in a linear regression setting. Our bound is model dependent in the sense that it's allowed to consider properties of this linear prediction rule and the sample size and some probability that we're allowing things to fail. It's a uniform bound if for all nicely sub-Gaussian distributions where we've got our excess risk bounded by this thing. Okay, so, you know, it's a bound that's good in that sense. We don't want, one thing we need is that it shouldn't be kind of ridiculous as a function of the sample size, that it's, we say, bounded anti-monotonic. So if you double the sample size, you might expect as you increase the sample size that our bound should get better. We just insist that it doesn't get more than a constant factor worse if you have a constant factor increase in the sample size. So, you know, seemingly a mild condition. And there's this notion of denseness of a set. You know, let me talk you through that in the result. Okay, so this is joint work with Phil Long. The result is that there's a sequence of distributions, very nice distributions, Gaussian X, linear plus sub-Gaussian Y, so that for any bound of this sort that's allowed to look at properties of the prediction rule that's guaranteed not to increase too sharply with the sample size, the least norm interpolant is, you know, is good in the sense that the excess risk is going down like 1 over square root of the sample size, you know, so that's great. But the set of sample sizes for which it's a terrible bound is, you know, almost all of them, is some significant fraction of the n. Right, so with high probability, this bound, which is supposed to be bounding something that's going down like 1 over n, is as big as a constant. Okay, so you know, anything of this flavor that's only using properties of the prediction rule is guaranteed to fail. So it's kind of ruling out a whole class of analysis methods for these kinds of problems. As I say, these are quite natural joint distributions, you know, Gaussian and sub-Gaussian conditionals, and you know, it's any model dependent bound that doesn't increase too quickly with a sample size. Okay, I'm going to skip over the proof. The proof idea is sort of based on the observation that if you have a fixed design, then interpolation is a bad idea. You're going to be noise level away from the truth, right? You know, this is what you should be predicting. If you're interpolating, then you're order of the standard deviation of the noise away from where you should be. And, you know, we can leverage that to show that any bound that's that's going to be valid in this sort of setting is going to be terrible in a benign overfitting setting, and you can make those two indistinguishable. Okay, so let me summarize. So we're looking at these overfitting settings where we're far from the regime of the classical regime of a trade-off between fit to training data and complexity. We saw that in linear regression, having this long flat tail of the covariance eigenvalues is necessary and sufficient for good prediction of the minimum norm interpolant. The intuition there is we've got this noise hidden in lots of unimportant directions, that the linear function in those other directions is spiky, but not, but has a small L2 footprint. So you need lots and lots of unimportant parameters, a large number compared to the sample size. It's important, seemingly, to have finite dimension. You know, infinite dimension, we have very specific conditions on the eigenvalue decay, but it's much more of a generic phenomenon in finite dimension. It's necessarily leads to huge sensitivity to adversarial perturbations in this linear regression case. We can extend that across this spectrum from interpolating through under-regularized through to, you know, classical levels of regularization. And we saw that there are, you know, pretty strong limitations on any model-dependent bounds in understanding these kinds of phenomena. In terms of open problems and future directions, I mean, you can say something about the neural tangent kernel kind of case regime for deep networks. You can think of that linearization in these terms as, you know, solving a linear regression problem. Our results don't apply directly there because of the sub-Gaussian condition. We need things to be sub-Gaussian in that reproducing kernel Hilbert space. But, you know, it turns out you get the results that are known for special cases where you have, you know, Gaussian distributions and very specific, you exploit specific properties of the kernel. Then, you know, in those cases, the asymptotics point to exactly the same picture of K star dimensional subspace and another orthogonal subspace that's got a huge number of small eigenvalues. You know, we're seeing exactly the same split into the prediction component and the interpolation component in that setting. Although, as I say, these theorems aren't directly applicable because of the technical conditions. But I think going beyond that linear regime is really interesting. You know, what's going on in these, you know, when you're in the sort of essentially non-linear regime for deep networks. I think that's a very exciting direction. Okay, and these are some pointers to the papers, and I'll stop there.
Thanks, Peter. So I'm just going to quickly summarize the things. So I will, if you can stop sharing, I'll share my slides. It's not a small amount, yeah. And then I will open it up for broader questions. So it's just. All right. So thank you very much for an interesting talk. I was trying to understand everything. So the questions is mostly because of that. So just a high-level overview, and I think I was going to touch on some of these things that you mentioned towards the end. And the puzzle is basically overparameterized neural networks seem to fit the training data very well, but still generalize well. And so, I mean, this is sort of trying to understand that phenomenon in a linear regression setting. And in some sense, from my very high-level reading of the topic, there are two sort of analysis methods. One is this neurotangent kernel approach, where there's some random initial condition, there's linear dynamics around it, some early stopping rules are done, and so basically the zero training error solution is found very close to the vicinity of the initial condition. And there's usually some appropriate RKHS to analyze the solutions. The other direction seems to be looking at a mean field type analysis, where you consider the width of the neural network to go to infinity to get some sort of PDE or some type of SDE. And right. Analyze the limiting behavior of that system to then comment on what's going to happen.
Right.
So the current work seems to sort of fit in between in some ways, and I'm not going to belabor these points. I think you mentioned it very well. So I'll switch next to sort of thoughts and questions. So at a high level, the result seems to be a combination of the two, and this is at least from my perspective, and I could be wrong. So the linear regression setting is appropriate with the neural tangent viewpoint, but that usually looks at early stopping type criteria, whereas it seems like what you have is more like an asymptotic solution. Is there a way to reconcile these two viewpoints, or is that not the right way to think about it?
So the neural tangent kernel, this linear regime is not, I mean, okay, so I guess it depends kind of crucially on what loss you're talking about, but, neural tangent kernel, if you have a loss like the quadratic loss where the solution is not at infinity, then it's really a regime where, your initialization is such that you'll very rapidly converge to a global optimum. There's no early stopping required there,
Okay.
and that global optimum, of course, is a perfect fit to the training data. So yeah, I mentioned that at the end, that's very much this setting. That neural tangent kernel is a particular nonlinear function of the kernel in the input space, the linear kernel in the input space. That nonlinear function depends on the initialization and the network in between, but it's some fixed function, and those results that I mentioned for let's say Gaussian input distributions, they're talking about excess risk in that sort of setting and getting qualitatively, very similar answers.
Okay.
I guess they're asymptotically exact. But yeah, the in terms of the asymptotics of the gradient, you're really going to a global optimum in a short distance, so that the linearization is accurate across that full path of the gradient flow.
Oh, thank you.
Right. So I'm not sure, I don't think there's any early stopping piece to that story.
Okay.
The thing that I think is the most interesting is getting away from that linear regime, where your initialization is not so large, or the situation is not such that, a linear approximation is good. You do have to travel far in parameter space. What can we say there about this same phenomenon?
That seems to be the side that the mean field analysis seems to concentrate on, but with the
Right.
a certain asymptotic dimension, it seems to be.
Right, and that analysis demonstrates we're really it's in quite a different it's quite a different world from the NTK world, right? Things look really very different there, but I don't know of any work in that asymptotic regime that's really talking about this same phenomenon, benign overfitting phenomenon.
So
I think that's
you
very
ignore some of my other questions. In some sense, the last sort of thing is, how should I think about these results in decision making, say in the deep RL context? You're in the sense that you could think of those labels as a policy that is given me that label noise or whatnot, and then based on what I learn, I adapt something. How would that? How should that be thought of in this context?
I think that's a really interesting direction. I've been thinking a little about the dynamical systems settings. So more estimation than the analogous prediction problem in a setting with dependence rather than the control problem. But yeah, I think then what can you say about an adaptive control kind of setting? And yeah, I think that's a very interesting direction. I don't have anything intelligent to say about that beyond I don't know. But yeah, I think that is really, really fascinating direction. Something I'm kind of
stop my thing. Stop my. Oh, okay. And I'll open it up for questions. I guess I didn't share my thing. That's okay. I was just reading off some questions. So, yeah. So I'll open it up for questions. If anyone has any questions, please ask Peter.
Hi, Peter. Thank you for the very insightful talk. I was wondering, is there an analogous upper bound if we consider like the same generative setting, but we consider hard margin SVM? Is there some kind of upper bound using effective rank, maybe on the margin, or maybe like a soft margin SVM, some sort of bound like of that sort?
Yeah, so so I've seen asymptotic results of that flavor, you know, using random matrix theory tools that, and Andrea Montanari has some results of that sort, I think with Song Mei, perhaps, but you know, again, this kind of setting that you have let's say Gaussian inputs, and you know, you're interested in the asymptotics as the sample size grows together with the dimension, and then work out exact asymptotics of that sort of sequence of solutions to those kinds of optimization problems. In terms of the case of so I guess that's ends up being a hard margin SVM, right? A soft margin SVM is sort of outside of the you know, interpolation regime. So you know, then you're getting into more classical trade-offs between, right? If it's a soft margin case, then it's a more classical trade-off between fit to the training data and the norm of your norm in the RKHS. So yeah, I mean, I think that there are results that have very much the same flavor for the hard margin SVM in this asymptotic setting.
Thank you.
Any other questions? Yeah, go ahead, Nachmi. Yeah,
I can ask you a quick question. So at a very high level, you were getting at saying, okay, overparameterization is good for generalization, but not necessarily for robustness. Was that a right interpretation of the adversarial example? Right.
I mean, I think maybe, you know, it's not that it's overparameterization on its own, right? In the sense that you can have robustness in an overparameterized case if you do the classical, you know, follow the classical regularization story. But it's this combination of, you know, no regularization beyond just picking the smallest norm thing that fits perfectly. And together with overparameterization, which by the way is necessary for that no regularization approach to work, then that combination, you know, yes, it's inevitably non-robust in the linear regression setting.
Can you say a little bit more on how do you recover robustness? Like,
so in this setting, if you were to consider a ridge regression sort of solution with a classical level of regularization, then, you know, you have a nice strongly convex criterion that you're optimizing. You can talk about its behavior as a function of all sorts of perturbations, and you know, strong convexity kind of buys you a lot in that case. So, you know, you won't see the same phenomenon if you were to work with ridge regression.
Okay.
All right, that's all I meant. Which can be very high dimensional, of course, right? So it's not as if you know, you're doomed to this non-robustness if you're in the non-parametric world of having the dimension massively exceeding the sample size, right? It's just if you do this kind of crazy thing of fitting to the noise in this high dimensional world, in the linear case at least, you know, it's clear that that's inevitably going to lead to non-robustness.
Thanks.
And, you know, I wouldn't be surprised if that were a more general phenomenon, right? I mean, you know, it's sort of obvious that interpolation is going to be a interpolation with good generalization is going to be a non-robust thing locally around the sample points. because those points are, noise distance away from where they should be, and you're predicting accurately, which means, for most points under the distribution, you're not noise distance away from where you should be. So there's got to be a sensitivity at those sample points. But actually for deep learning, it seems like there's a sensitivity much more generally. You don't have to look at a point that was in the training sample to find a direction where you're hugely sensitive to changes in that direction. Which is qualitatively the nature of the linear case, right? It's not as if you're restricted to sample points to find this sensitivity. Any point in the space, I mean, this is just because of linearity, right? But any point in the space, of course, you find the same perturbation direction will lead to huge changes.
So I had a question along those lines, again, just following up. So in the case where the analysis is has direct consequences to the NTK type approach, is it possible to identify these adversarial directions, and does that actually correspond to what happens in practice or not? I mean, in this case.
Yeah, that's a good question. I mean, you could consider the NTK, in the neighborhood around the solution, and understand. Yeah, I don't know, I guess is the short answer, right? If you're taking a local linear approximation, then the hypothesis would be that there's a vector that's kind of the transformed version of the noise vector in the sample that corresponds to a direction of sensitivity. But this is a local linear approximation. Yes, so just the existence of these adversarial perturbations, already is exactly that property, right? That as you move around through this space, you're going to see directions not necessarily the same. So I guess there's nothing to distinguish that situation from the just the existence of those directions.
I guess it's not clear that there is a common subset of directions from there that you can pull out.
That's true, and that's another empirical phenomenon that's pretty surprising, right? That the existence of these universal directions that you can find directions in input space that are pretty effective for perturbing the output across a very broad set of input examples, which does look like a linear kind of phenomenon, right? Or you'd certainly see that in the linear setting. Yeah, and I think that's a very surprising thing. Yeah.
So any more questions from anyone? If not, let's thank Peter once again for an excellent talk and answering all our questions.
Thanks very much.
Thanks again.
All right, sure.
All right.
See you.